Welcome to Math with Malia. Today we're going to cover Savvas enVision Algebra 1, Topic 10, Lesson 7, our last lesson in this topic. And we're going to be learning about inverse functions. After this lesson, you'll be able to use inverse functions to solve problems, and you'll be able to define what an inverse of a function is. Here's our explore and reason. The tables of data show food orders for different parties. Pizzeria A has pizzas ordered compared to sandwiches ordered, and Pizzeria B has sandwiches ordered compared to pizzas ordered. So you notice that the variables, or what the variables are defining, are switched. What kind of functions do these tables represent? Well, if I'm looking at the x values for Pizzeria A, I can see that they are increasing by 2 every time. And the y values are decreasing by more or less 3 every time. So that appears to be pretty much linear. Pizzeria B, while the variables are switched, the x values are increasing by pretty much 2 or 3 every time. And the y variables are decreasing by 2 every time. So again, that appears to be linear, more or less. But the variables are switched. So this is what we mean by inverse functions. The inverse of a function reverses the order of the outputs and inputs of a function. The inverse of a function f is usually written as f to the -1, okay, or f inverse. So if f of x equals y, remember our outputs are represented by f of x, then f of inverse, the inverse of f, or the inverse of y would equal x. So we just switch the inputs and the outputs. We just switch x for y. For all the x's in the domain of f and all the y in the range of f. So a function has an inverse function if and only if the original function is a one-to-one, meaning one input gives only one output. So a way you can figure out what the inverse of a function is you can make tables. So here's our table for f of x. Okay, notice our x values are 0, 1, 2, 3, and our y values are 6, 8, 10, 12. For the inverse, we just switch the inputs and the outputs. So we switch the values for the outputs and we put them in for the inputs, or the x values. And the values that were originally for the x values, now we will put for the outputs, or the y values. So all we did was switch the values for x and put them in for the values of y. So remember, a one-to-one function is where one output only comes from one input. Example 1, understanding inverse functions. What is the inverse of the function f of x equals 2x plus 6? This is the same function we had in the table. We can see that it is linear. It follows our slope-intercept form, y equals mx plus b. So we know that our slope comes from the value in front of the x. So our slope is 2 for our original function. And we can find the slope of the inverse function. So slope usually is the change in y values over the change of x. Well, if I'm going to find the inverse, I'm going to find, so the inverse slope would just be the change in x values over the change in y values. Okay? So if we had a table, I'll copy the table over here, and we can just pick two points. Okay, so this is the original table. When x was 0, if I plugged in x into my original function, if I plugged in 0, 2 times 0 plus 6, my y value is 6. And when x is 1, my y value 2 times 1 plus 6 would be 8. So this is the original function. And then if we switch those, we're going to put the change of x, or 1 minus 0. So we're going to put the x first, and then we're going to put that over the change in y, 8 minus 6. So what do you notice about the inverse slope, or the slope of the inverse function? It is the multiplicative reciprocal of the original slope. Okay, so now that we have the slope of the inverse function, we can plug that into point-slope form and then use one of our values. Remember, we switched them. So then the x value would be 6 and the y value would be 0. And we put them in point-slope form and simplify, and our new function would be 1/2 x minus 3. So the inverse function would be 1/2 x minus 3. So it might help. I'll just write the new table again. It was on the previous page, but just in case, when we switched the inverse, this is f inverse function, we just switched the values. So here, the point that we used for point-slope form was 6, 0, and that's how we get our inverse function in slope-intercept form. So how is the slope of the inverse function related to the slope of the original? Well, we already said the original slope was 2, and the slope of the inverse was 1/2, and 2 and 1/2, they are multiplicative inverses. Meaning, if I multiplied them together, if I multiplied the multiplicative inverses together, I would get 1. Okay, example 2, graphing an inverse function. What is the graph of f of x when it is x squared for x is greater than or equal to 0? So we do have a restriction here. And then what is the graph of the inverse? Okay, so this is the parabola, but we only want positive values of x. Okay, so we're only doing this right side of our parabola. It is upward facing. It's our parent function, but we're only doing the values that are to the right of the y-axis. So since the original function is restricted, then the inverse function will also be restricted to only those positive values. So we can write our tables first. I'm going to zoom in. We can write our tables. Here's our original function. Just plug in values for x and get your outputs. We're just squaring the x values. And then since the inverse, all we do is switch the outputs for the inputs. So again, our values that originally were for the y values are going to be in our column for our inputs. Okay, so we just switched those. And now we're going to graph. We have our points, 0, 0, 1, 1, 4, 2, 9, 3. We can graph those 4 points. And there's the graph of our inverse function. Okay, so if the domain of the original function were not restricted, then we would have the other half of the parabola. But the inverse then would not be a function, right? If we were to continue that, it would not be a function. It would not pass the vertical line test. So this is why we have to have that restriction for the original function, for the inverse to fit the definition of a function. So notice we also have a line of symmetry between the inverse and the original function. If we were to fold along that dotted line, that line of symmetry, which is just y equals x, then our original function would match up with the inverse. So it is a reflection along the graph or along the line y equals x, okay, that linear line of symmetry. Okay, let's do the example 2. Try it. Graph each function and its inverse. So for part A, we can see that we have a linear function for our original function, and we can identify the slope by the coefficient in front of the x. So we know the slope would be 3. And remembering our relationship between slope of functions and their inverse, we know the slope of the inverse function would be the multiplicative inverse. So the slope should be 1/3. How can we graph this? Well, like we did in the example, we're going to make some tables. So here's a table for f of x, x and y. I like to go a little bit to the left of 0 and a little bit to the right of 0 for my input values. We can choose our input values. So let's start with -1. When x is -1, if I plug it into the function, my output would be -5. 3 times -1 is -3, minus 2 is -5. When x is 0, plug it into the function, our output would be -2. When x is 1, 3 times 1 is 3, minus 2 is 1. And let's do one more just for fun. When my input is 2, plug that into the function, my output would be 4. So from that, we can graph it. And I'm going to show you on my graphing calculator app that I have. So just going to your TI-84, if you have your graphing calculator, we can type into our lists. Since we have a table, go to Stat, Edit, our list, and you can see I have list 1 is my X values from the table, and L2, my list 2, is the Y values for the table. And since we're using our list, we're going to use our stat plot function. So I'm going to make sure that my plots are on by going to second stat plot. Okay, plot 1 is on, and I can see that it will be a blue line. My X list is coming from L1, and my Y list is coming from L2, so this will graph the original function. And plot 2 is also on. I wanted to turn them both on. This one will graph a red line. Notice what's different. I made my X list coming from L2, which is the original Y value. So all I did was switch L1 and L2. That's like switching the values in the table. So I can graph both of these at the same time using my graphing calculator, using the same two lists. I just make sure to turn the different plots on and make sure that the lists are switched. So we can see that the original function in blue has that slope of 3, and the inverse function in red has a slope of 1/3. Okay, let's do part B. This function is a quadratic function, so we will have a parabola. We can see that it will be upward facing since our leading coefficient is 2, and we do have a limit. We're only going to be looking at positive input values. So let's make our table for the original function, and we're only going to choose positive input values. And we're going to see why. Just like in the previous example, we can only choose positive input values. So let's start at 0, 1, 2, 3. That'll give us 4 points to graph. If I plug in 0 into my function, my output would be 0. If I plug in 1, 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. So we have our points that we can plug into our graphing calculator. So going to your graphing calculator, go to Stat again. We'll edit our lists. List 1 will be our original input values. I'm going to add a couple negatives just so we can see why we have to have that limit. But we had 0, we had 1, we had 2, and we had 3. Our output values for these values would be 8, 2, 0, 2, 8, and 18. And just like we did before, our stat plots are on for these two lists, and the only difference is for plot 1, which will graph the original function, I have my X list coming from L1, or my inputs coming from L1, and my outputs are coming from list 2. And for plot 2, we still have it changed. So now my inputs are coming from list 2 and my outputs are coming from list 1. Since it's an inverse function, we switch the inputs and the outputs. So let's graph it. And we can see where I have included the negative points. Okay, so I've included the negatives so we can see the red function, the inverse function, is not actually a function because it will not pass the vertical line test. Okay, so if we go back and change our list and we take out those negative values, and so we're just going to do 0, 1, 2, and 3. Then we can see our inverse function, and the red graph does fit the definition of a function. So this is why we have to be careful of the limits for quadratic functions and their inverses. We can only have positive values of the original function so that our inverse function will also be a function. Example 3, find the inverse of the function algebraically. So besides using our graphing calculator, can we find the inverse? Well, yes, this is pretty easy. Remember, in the tables, we switched the output values for the input. So we switched the y values for the x values. We're going to do the same thing to the equation. So here's our original equation. Y equals 2x plus 6. There's our linear function. All we're going to do is switch y and x. So that's what we did. We switched places for x and y. And then we just solve for y so we can have our function equation in slope-intercept form. So I'm going to subtract 6 from both sides and then divide by the coefficient 2. So divide everything by 2. Divide 6 by 2 gives me -3. And 2y divided by 2 gives me y all by itself. So now our inverse function is written in slope-intercept form. It's pretty straightforward. Just switch the x and the y and then solve your equation for y. So it is in slope-intercept form. Okay, let's try it. Find the inverse of each function. We're going to do that algebraically. Remember, we just switched the x and the y. F of x is the same as y. So I'm going to switch places. So it becomes x equals 3y squared, and I'm going to solve for y by doing opposite operations because of the property of equality. Divide both sides by 3. Leaves me y squared equals x over 3, and then take the square root of both sides. So y equals the square root of x over 3. For part B, same thing. Y equals x minus 7. Switch places with the inputs and the outputs, and then solve for y. This one was pretty easy. Y equals x plus 7. There's our inverse function. All right, well, how do we apply this to real-world application problems? Keenan plans to fly 1,097 miles from Miami to New York City to help assemble a dinosaur exhibit at a museum. He wants to use the miles he earns from his credit card purchases to pay for his flight. How much will Keenan need to spend in order to earn enough miles for the flight from Miami to New York City? You can see in the graphic that he earns 1 mile for every $10 he spends, and after his first purchase, he already has 500 miles as a bonus. So if we were to formulate our function that represents the balance of air miles he has, f of x is the balance of miles. It would be represented by the miles per dollar spent times the amount spent plus the bonus miles. Okay, so since he earns 1 mile for every $10 he spends, the inverse of that, okay, so we're thinking of inverse functions. The inverse would be that he earns 1/10 of a mile for every $1. So all I did was I switched the values, right? So we're thinking of inverse functions. So he will earn 1/10 of a mile per dollar. And if I multiply that by x, which would be the amount of dollars spent, plus the number of bonus miles, we will have how many miles he has left. Okay? So we're writing the inverse function. That would give us y equals 0.1x plus 500. To write the inverse function, we need to switch the inputs and the outputs, so switch x and y, and then solve for y. So subtract 500 from both sides. That's what we did here. And since we have 1/10 y, we can get rid of that 1/10 by multiplying everything by 10. So that's what we did here. We multiplied everything by 10. And that gives us our final inverse function, y equals 10x minus 5,000. Okay, so our inverse function, the inverse function is 10x minus 5,000, okay, where x represents the number of miles. Okay, and we can use that then because we know how many miles he has. He's going to use 1,097. So if we use that inverse function to evaluate for 1,097 miles, we can plug that into our function and solve. He will need to spend $5,970 to earn enough miles for his trip. Okay, so our inverse function was solving for the amount of money spent. The original function was telling us the balance of miles. So again, we switched the input and the output, and instead of calculating total miles, we were calculating total amount of money. So we were switching our input values and our output values. Okay, let's try it. Suppose the credit card company changes the program and says that he earns 1 mile for every $8 he spends. How would that change the amount of money that he needs to spend to earn the miles for his trip? All right, so our function would be representing the amount of miles earned per dollar. Okay, so miles earned per dollar, or 1 divided by 8, is 0.125, plus our bonus of 500 miles. Okay, so we had to figure out miles per dollar, per $1. So we did 1 divided by 8. So here's our original function. We're going to find the inverse function by switching x and y. So I'm going to just say this is x, and this is 0.125 times y plus 500. Okay, and now again, just like we did before, we're going to solve for y. Subtract 500 from both sides. Okay, you can do this a different ways. You can just divide everything by that coefficient, or you can clear the decimals if you wanted to, but let's just go ahead and divide by the coefficient. So that would give us y equals, if we calculate, 1 divided by 0.125 would be 8x, and 500 divided by 0.125 would give us 4,000. So there's our inverse function. And again, same number of miles, so we're going to evaluate when x equals 1,097. Eight times 1,097 is 8,776 minus 4,000. So he would have to spend $4,776 to earn enough miles for that trip. All right, you've made it to the concept summary for inverse functions. The key to inverse functions is just to remember to switch the input values for the output values. And then your final equation for the inverse function, you need to solve for y and get it back into slope-intercept form. If you have any questions, put them in the comments, and I'll see you back here for topic 11.